Hello and welcome everyone. I am Ahmed Al-Sharabasi and I will present today in this video a short introduction about openEMS electromagnetic solver. It's a free and open source software based on finite difference time domain method. First, you could Google it about openEMS and then you can easily find the website openems.de. After logging to the website, you directly will be in the downloading page, as you can see right now. It's available for Windows and Linux operating systems, and also some news and announcement about the latest versions are available. I am downloading right now the version for Windows 64-bit. For other versions, you can find it in the older version. After downloading z.zip file, first unzip this file to be extracted in a folder, and it's recommended to rename this folder as openEMS without any more words or letters, as this will be used the main folder for the whole simulations later. And after extraction is being done, you can go now and open MATLAB, and in MATLAB you can write down in the workspace add path the directory where you bought openEMS and then /MATLAB, and then you may let the workspace folder to be the same. And by returning back to the downloading web page, just click on download and install on the top of the left column, and then you will be redirected to the openEMS introduction web page. In this web page you may find that the openEMS, as we mentioned previously, it's a free and open source based on finite difference time domain solver. And some of the features are presented here right now. You can see it's an efficient finite difference time domain solver for 3D Cartesian and cylindrical components as well. And one of the most used components in this software is the C++ library that describes the geometrical objects and the physical and non-physical properties for these structures, and it's called CSX-CAD. And from the installation part, as we can see here, for Windows, the 3 steps we have performed before: downloading, unzipping, and adding the path for the MATLAB. And just to remind myself and all of you, as there is some honesty in this software, it's a free and open source, but we have to refer every bit of work to the people and guys who implemented this software before. And now let us move and see basically how this software works. And you can click on the online manual, and then we can see in this web page, like there is some setup at the beginning of the simulations, like this order in MATLAB, the finite FDTD equal initiate FDTD, and CSX initiate CSX. So both one of them for the boundaries and for the time simulation itself, and the second one for defining the geometry and the properties of the materials. And then there is a properties for the structure to be simulated. So some of these properties are physical, like the material type, and other are non-physical, like the probes and dumb boxes. And then the primitives, which are the building blocks representing the structure to be simulated, or even the field sources or the field dumps. So each primitive has a shape, so like box, sphere, cylinder, and a physical property defining its function, or a non-physical property. And third, with respect to the finite difference time domain solver with the mesh grid, the openEMS supports a fully graded mesh in Cartesian and cylindrical coordinates, and this mesh can be smoothed at the end. For the field excitation and ports, there is a variety of field sources. These field sources can be lumped port, waveguide port, many sources. And for the last thing, for the field dumps, which are used to define the coordinate where the field saved during the simulation. At the end, there is a near field to far field transformation that can be used in calculations of far field in some of the applications like the antennas. If we go down until the bottom of the page, we can find the list of the function, and then we can open it so we can see right now a fully alphabetically sorted list for all functions used in openEMS. The one in blue, they have some further comments and help about each function. By returning back to the introduction web page, we can click on overview and see some further details about these functions in the openEMS. So we can see by order the physical properties and non-physical properties and the primitives. So the primitives used, there are some of them: the box, sphere, spherical shell, cylinder, cylindrical shell, the curve, wire, polygon, extruded polygon, and some other general like the polyhedron in 3D. If we can see through the primitives, we can now see the first 7 or 6 ones till curve or wire, the most common and used in the whole structures. Other things we can see here in general, like the ports used to excite the structures. There is a lumped curved microwave ports and circular waveguide and rectangular waveguide ports. And also there is near field to far field damp setup just to get some behavior of the antennas. And there is the meshing different ways, and there is some booster processing to find voltage and current and S parameters. So we can start by how to define the material first. So in the description you can see the first order CSX add material, CSX, and the name of this material. And the main properties will be used. It's the epsilon, mu, kappa, and sigma, which is the relative permittivity, epsilon, and relative permeability, mu, and kappa is the electric conductivity, and sigma is optional. Maybe you are not using a lot in this simulation. So the first 3 things are the most important ones. So after getting these values, you can write down CSX, set material property CSX, and the same name like above, and then the variable argument like epsilon, mu, and kappa. And take care about the letters, capital and small ones. And then an example for this, like CSX add material, CSX, and material name. So the material now, it's called material name. And CSX, the second line, set material property, CSX, and the same material name, and epsilon, which is the relative permittivity, equal 10.2, and mu, which is the relative permeability, equal to 1. So this is our new material that can be used to describe one of the structures. And let me remind you that the material name in both MATLAB commands has to be the same. And then we can move forward to the second property, which is the metal property. So the command line in MATLAB could be written as CSX add metal, CSX, and name of this metal if we are speaking about a perfect electric conductor. And if it's a lossy conducting material, we can add the conductivity value and the thickness of this material. So an example for both of these commands, CSX add metal, CSX metal, so it means this is a perfect electric conductor material. And then the second one, CSX add conducting sheet, CSX copper, the name of the material, and the value 10 power negative 6 is the conductivity, and the value 10 power negative 6 is the thickness of this material. Another property, which is the excitation, which represents the input signal coming to the structure to study its behavior. So first we have to differentiate between the time and the space properties for this excitation. With respect to the temporal excitation like sinusoidal and Gaussian, which represent by the central frequency F naught and the FC, which represent half of the bandwidth around this F node. And we can also may describe another custom excitation, which is not sinusoidal or Gaussian. All these temporal excitations are related to the finite difference time domain solver itself, so each function will include FDTD in each combination. Regarding the other part of the excitation properties, which are the spatial properties, is related to the CSX functions. So each function will include CSX in the MATLAB command, as we can see right now. Some of the structures required the total and scattered field excitation, so there is a MATLAB command that like CSX add plane wave excite, and we have inside this command the CSX first and the name of this excitation and the K direction, E direction, and F node and variable arguments. One example that showing a Gaussian pulse as a total field scattered field source as a plane wave, which is in time domain is a Gaussian excitation. We can see through the beginning there is a FDTD function represents the Gauss excitation, and then CSX, it's a plane wave excitation, represent where this excitation would be applied. As we may see in the second example, that we have a finite difference time domain function at the beginning, set sinusoidal excitation, FTT and F node, and then CSX add excitation CSX, and there is infinite dipole and 1 and vector with 1 0 0, and there is a starting point and the starting and stopping point, and then the function CSX add box, which we'll see later how this function work. From the beginning, in the CSX add excitation, there is a number which is 1 and the vector 1 0 0. You can go up again to the description of this function, how this function works, add excitation. The one here represents the excitation through E field hard excitation, and there is another vector 1 0 0. There is like the example here, it's which excite 2 0 0 in the vector represents a 2 volt per meter electric field in X direction. So now this 1 0 0 represent 1 volt per meter excitation for the E field in the X direction. The last two properties which are used to implement how to measure the electric magnetic voltage or the current through the whole structure. The first one is the field dump, which is the command like CSX add dump CSX name and variable argument. In this argument we can define the dump time as 0 for electric field time domain, which is the default, or 1 for H field, which is a magnetic field in the time domain. And there are many variables as we can see right now. An example for this, we can just define CSX add dump CSX AT, so the name of this dump box is AT, and describes the dump box in the second command line. Another example which is add X CSX EF dump type 10 and frequency, and there is range for this frequency as a vector. Dump type 10, as we can see further up, it's represent the frequency domain electric field measurement. And the second property to record voltage and current at certain points are the probe box property, which are useful to get the values at certain points, not the whole space like the dump box. And now we coming to the end of this first part of the introduction, and see you later in part 2 in this introduction. And thank you.